Welcome. This clip is about convergence, which I call the most basic idea, the most fundamental idea in calculus. Now, if you've had Calc 1, you've learned in the first chapter about the limit. And you might think that's the most fundamental idea. But the limit definition uses the definition of convergence twice, and it uses it in two slightly different ways. So I would say convergence is the most fundamental idea in calculus. Once you understand convergence, understanding the limit is pretty easy. So let's begin. All right. This kind of recaps what I just said. So let's explore the idea of convergence. You learned this in grade school. And what does this mean? It means that if you write 0 point and you write an infinite number of 3's, this is just two ways to symbolize the same thing, that it equals 1/3. Well, if you think of adding an infinite number of 3's as a completed action, as a done deal, then maybe the equal sign makes sense. But suppose we think of adding the 3's as an ongoing process. We've added a whole bunch of 3's, but we still have more to add. You can never quite reach infinity. Let's think of it that way for a second. Then the equal sign wouldn't really be correct. This is where the idea of convergence comes in. We could imagine that this, with the dots, as in the process of being completed, we've added a gazillion 3's, but we still have more to add. So we would write that this is getting closer and closer to 1/3. It's approaching 1/3. It's converging to 1/3. Now we can think each of the separate numbers, we can separate them out. We could say we start at 0.3, and then we add 1 3. We add another 3, and we add another 3, and we keep going, and we converge to 1/3. And this is what we'll call a sequence. Okay. Now I have another example of convergence. Here we have a stick of length 1. Cut the stick in half, bring the first half down. So what we've brought down has a length of 1/2. Now we cut the remaining piece in half. And that means we have a piece of 1/4, and we bring that down. We cut the remaining piece in half, and we bring that down. Now we have 1/2 plus 1/4 plus 1/8. We cut the remaining piece in half, and we bring that down. Now we have this. You'll notice that the total length is going from 1/2 to 3/4 to 7/8 to 15/16. And it's easy to believe that this total length is getting closer and closer to 1. Now, we want to make the idea of convergence mathematically precise. So what do we need? We need a few things. Well, first of all, we need a sequence. So here's a sequence. Here's another one we've seen. And for convenience, we'll give the sequence a name. So when we write this, we mean n is going from 1 to infinity, and here's a of 1, and here's a of 2, and here's a of 3. When we write this, we mean that b of 4 is this, and b of 6 is this. So if you were to see b of 6 instead of n, it would mean this term. And this symbolism just defines the sequence. And once we have the sequence defined, we can say, hey, the sequence an is converging to 1/3. Or we can say the sequence bn is converging to 1. So we can write it that way, or we can write it this way. So either symbolism means the same thing. It means that the distance between the terms of an and 1/3 is getting smaller and smaller. That an is getting closer and closer to 1/3. Similarly, it means that the distance between bn and 1 is getting smaller and smaller. So if we want the distance between this sequence and 1/3 to be less than here, we've got to add about what? 10, 12 3's, however many there are we need. And if we want the distance between this sequence and 1/3 to be less than that, we've got to add about 500 3's after the decimal point. Then we'll have 0.3333, we have about 500 of them, and that will be within this distance of 1/3. Maybe we need 501 3's, I didn't count precisely. Now here's our definition. We're going to let the Greek letter epsilon stand for some small number. And we're going to say that when we write something like this, or like this, or here, or here, we mean that this distance gets smaller than any positive number we care to name. It gets smaller than this eventually, or this, or this. Similarly, this distance between the terms of Bn and 1 gets smaller than this, and this, and this. Right? For any epsilon we name, if we take n large enough, this distance is going to be small. It's going to be less than epsilon. Okay? So let's just take an example of this. We're given this sequence. Here's another sequence. And when we write out the first few terms, we see it equals this. And for n of 1, it's this, 2, 3, 4. Okay. Now we can see that this sequence is getting closer and closer to 0. So we could write this, or we could write that. By the way, here's a philosophical point. This symbolism seems to suggest that the process is ongoing, that we're still adding, let's say, 3's in that 0.33 example. And we're still striving to get there. This symbolism seems to say we've added all the 3's we need. We've added an infinite number of 3's, and the train has arrived at the station. In other words, we're at, well, in this case, that we're at 0. Not quite, because the limit, well, the case could be made that this also has the idea of an infinite process, ongoing process. But anyway, it's a philosophical point. Mathematically, both symbolisms are defined the same way. And here I'm lying to you, but I'm going to correct that in a second. Both symbolisms mean this. It means that as long as we take n large enough, this distance for this sequence becomes small, as small as we like. Well, what am I lying about? Well, I have to add one more little detail. This definition has to be fixed up a little bit. Now, we'll come back to it in a second. Look at this sequence. We don't want to say that this sequence converges to 0. It doesn't converge to anything. But with our previous definition, we could always find an n such that this is true. Right? There's always some n such that we can get as close to 0 as we like. But the problem is we keep oscillating. So what we want to say is, see, because this isn't true for all numbers bigger than Rn, so what we do is we require that. We say, look, this, we write this, and we mean that this is true for any number bigger than a certain n. So you'll remember, if we want to say that 0.333 converges to 10 to the negative 500, if we take n to be about 501, then any other number of the sequence bigger than a to the 501 is going to be within this distance. This is a subtle point, and it's only meant to rule out this. Okay? We don't want to say that this converges. It doesn't. It oscillates. So we need to say for anything bigger than this n that this is true, not just for some number bigger than this n. So you may need to think about that a bit, but that's basically what's going on here. Well, are we done? Well, here anyway, here's the real definition of convergence. We write this, or we write this, when this is true for any e and for any m bigger than n, as long as we take n large enough. Well, I'd like to say we're done, but we're not. We've got just one more wrinkle, sadly. Just another slight refinement. What about this sequence? Do we want to say that converges to 5 or not? Well, under the present definition, it does converge to 5. You can go back a slide and think about it, but it does. And this definition of convergence is used in one part of the calculus definition of a limit. But sometimes we don't want to say that this converges. So we have to make another slight modification to our definition. We have to say that the distance gets smaller and smaller than any epsilon we like, but is always bigger than 0. Now, you might think, wow, why are we doing this? Well, first of all, let's summarize what we've done. We're going to see both types of convergence in the definition of the limit. And I'll call it type 1 and type 2. That's my own terminology. It's not used widely that I've ever seen. Okay, type 1 convergence says that for a sequence like this, we can write that the sequence converges to 5 because we're using this definition. Type 2 convergence says for a sequence like this, we don't want to say that the sequence is convergent to 5, so we use this definition. We add this. Otherwise, both definitions are the same. This is the same. Now, this might seem kind of picky, but unfortunately, we need both types of convergence in the definition of limit. They're used. They're there. So let's take a look at that. Here's a standard definition of limit. And you'll notice that the independent variable x, we're using type 2 convergence. X is getting closer and closer to a, but we're not letting it equal a. For the dependent variable, f of x is getting closer and closer to L, and if it equals L, we don't care. That's the type 1 kind of convergence. Now, why is this? Let's just think about it a little bit. Basically, I want to talk about convergence, but I'm going to mention a bit about limit too. One way to understand this is in a general way that we need two types of, we need two types of convergence because we want type 2 convergence on the independent variable. But since the dependent variable f of x is dependent, we don't need to put it on there. It's taken care of by putting type 2 convergence of the independent variable. Well, that's kind of vague. Let's look at an example. We have a function. Now, we don't want to say the limit of this function at x equals 2, or as x converges to 2, is 1 or 2 or anything, because the limit doesn't exist at x equals 2. Yes, the left and right-hand side limit exists, but we're not talking about them. The actual full limit does not exist at x equals 2 for this function. So we have to use this definition of convergence on x. Otherwise, it would, if we weren't using this type of convergence, this function would satisfy the definition of limit at x equals 2, and we don't want that to happen. So now you have to think about that a bit maybe, but here's the kind of the upshot of all this. What happens at x equals 2 is irrelevant to the limit of f of x at x equals 2. What happens at x equals 2 is irrelevant to the limit as x approaches 2. In fact, f of x doesn't even need to be defined at x equals 2. Only what happens when x is close to 2 is relevant to the limit at x equals 2. Okay? Well, I could say more about the limit, but I'm going to stop here. I think I've accomplished what I wanted to say about convergence. Hopefully you have a better idea of convergence and of the limit idea. I'll just say one more thing about the limit in a nutshell. After the idea of convergence of the independent variable x is understood, the limit idea merely builds on that. We're given that x is converging to a, and then we're given a function. We're saying, well, what happens to the function? Does it converge to anything? So we just have to decide if the function converges or not. If we understand convergence and we are given that x converges to a, then it's just a mechanical process to see if the function converges or not. Okay, if you want to download or modify this PowerPoint for your own purposes, that's where it's going to be. And I hope you found this presentation helpful.